Welcome back. Now the problem that I'm going to do is related to particle physics and its relationship to relativity. So there's a bunch of problems that you can do involving particle physics, interactions of particles with each other, particle disintegration, particle colliding with another particle, and it involves the equations of relativistic dynamics. So it's the interplay of particle physics with relativity. So in this problem, we are given a scenario. It says a neutral particle decays into a proton and a negative pion, a neutral particle, and the particle is not traveling, it's just standing still, but it's a spontaneous decay of the particle into a proton and a negative pion. So the question that it's asking, it's also giving you one other information. It's saying that the proton has a kinetic energy of 5.3 mega electron volts. So the kinetic energy of the proton is equal to 5.3 mega electron volts. So now it's asking, what is the identity of the parent particle, right? The original particle. What is the mass? What is the rest mass or rest energy? Okay. So what are the equations of relativistic dynamics that are of relevance here? Well, I'm going to write down the equations of all of the relativistic dynamics. We have here momentum is equal to gamma m0v, right? So basically, it's similar to non-relativistic dynamics, but wherever you have an m, you replace it by gamma m, where gamma is the relativistic factor. Gamma is equal to, defined by square root of 1 minus v squared over c squared. Right? It's a relativistic factor, we call that. So regular momentum is equal to mv, relativistic momentum is equal to gamma m0v, right? Then we have here rest energy. We have m0c squared, right? So rest energy is the energy that a particle has even if it is not traveling. It's just by virtue of the fact that it has mass. This is the famous equation, energy is mc squared, right? Then we have the total energy of a particle is equal to gamma m0c squared, right? So if the particle is traveling, we can say it's kind of like gaining mass. So the rest mass is going to turn into relativistic mass, and we have E total is equal to gamma m0c squared. The other thing we can say is the total energy of a particle is equal to the rest energy plus the kinetic energy, right? So the rest energy added to the kinetic energy gives you the total energy, which is gamma m0c squared, right? So now we can come up for an equation for the kinetic energy. The kinetic energy is equal to gamma m0c squared minus E rest, which is m0c squared. So the kinetic energy is going to be gamma minus 1 m0c squared. Okay? And then we have E total is equal to this one. I'm going to circle the important equations. Then E rest, and then momentum. Okay? So it could be shown that when velocity is small, this equation turns into half mv squared, half m0v squared, right? So when v over c is a very small ratio, it becomes, and it turns into, this equation turns into half mv squared, which is the regular mechanics equation that we use in physics 1, right? We say kinetic energy of a particle is half mv squared, but relativistic kinetic energy is gamma minus 1 m0c squared, and gamma is this factor, right? The other equation to come up with is the equation for the relationship between momentum and the rest energy and then the total energy. Okay, so what is that relationship? It turns out that if I square the momentum, if I multiply the momentum by the speed of light, right, momentum times c, and then I square that, then I add that to the rest energy squared, then I get the total energy squared, E total squared. Okay? So could we give a quick proof of that? Let's see here. If I multiply this by C, right, gamma m0vc, then I square that, I add that to m0 squared c to the fourth. Does that equal to gamma squared gamma squared m0 squared c. So I'm basically squaring this one here, right? Gamma squared m0 squared c to the fourth. Okay? So could we prove that that's equal to each other? So let's see here. Gamma squared m0 squared v squared c squared plus m0 squared c to the fourth. Gamma squared m0 squared c to the fourth. So the m0 squared cancels. So far so good. Okay? Alright, then you have here c squared cancels with that. So I get here c squared and then I get here c squared. So if I can show that gamma squared v squared plus c squared is equal to gamma squared c squared, then that will work. Well then, if I take this and I keep this here c squared, and then I take the gamma squared to the other side, I'm going to have gamma squared c squared minus v squared. Right? So then I bring this down to the bottom, and I have here gamma squared is equal to c squared over c squared minus v squared, and then I divide everything by c squared. I get 1 over 1 minus v squared over c squared, and then square root, and then that gives me what gamma is, right? So now we have proven this identity. Momentum times c squared plus m0 c squared is equal to E total squared. So if an object has a rest mass of 0, what's going to happen? Okay? If the rest mass is 0. So what are those particles? Like the gamma radiation, gamma particle is has rest mass 0. Photon has rest mass 0. So if m0 is 0, right? So if m0 is 0, what's going to happen? It's still going to have momentum, right? You're going to have pc squared is equal to E total squared. Then you're going to have P is equal to E total over C. So what's going to be the total energy of an object that has no mass? So if I put here total, now gamma is infinity, right, for a particle like that, because photons are traveling at the speed of light, right? So gamma is infinity, and then their rest mass is 0, m0. So this is 0, this is infinity. So what is their energy? Well, their energy is given by Planck's constant, h, right, times F over c. So we don't really use this equation gamma m0 because particles with no rest mass have m0, 0, right? So this is just 0 and this is infinity because they're traveling at the speed of light. So we use the equation energy is frequency times Planck's constant. So the momentum of objects like that, such as photons, is hf over c. Okay? Okay, now let's come to this problem. So how do we solve a problem like this? A disintegration of a particle. So we have to conserve two concepts, two quantities. Linear momentum and also the total energy of the system is conserved, right? So if this object initially was standing still, it had momentum 0. So therefore the momentum of the proton must equal to the momentum of the pion, right? So momentum of the proton, it must equal to the momentum of the pion, right? That's one conservation. And then the energy of this, the total energy, must equal to the energy, the total energy of the proton plus the total energy of the pion, right? So we have that the total energy of this, since it wasn't moving, it was standing still, it's just going to equal to its rest energy, right? So E rest. Okay? So then that's going to equal to the energy of the proton, right? But the proton has kinetic energy 5.3 mega electron volts. So the energy of the proton is going to be what? The rest energy plus the kinetic energy of each one, right? So we can split this up. Now we can look up a data table of the rest energy of the proton and the rest energy of the pion, and the kinetic energy of the proton is already given to you, right? So the rest energy of that unknown particle must equal to the rest energy of the proton. That's equal to 938.3 mega electron volts. Okay, that's the rest energy of the proton. The kinetic energy of the proton is given in the problem, 5.3 mega electron volts. And then the rest energy of the negative pion is given by 139.6. 139.6 mega electron volts plus the kinetic energy of the pion. Okay? Well, if I add this to this to this, right, I get a total of, so there's two unknowns here. We don't know the kinetic energy of the pion, and we don't know the rest energy of the unknown particle, right? But then we come to the momentum equation. The momentum of the proton, right? Which equation are we going to use? We're going to use this equation, right? So it's equal to what? E squared minus m0 c squared square root divided by c. So that's the momentum of the proton, right? And then that's going to be equal to square root the total energy of the pion minus m0 c squared over c, right? So since momentum is equal to E squared minus m0 squared over c, right? Then square root. So now the c and the c cancel, and I don't even need the square root, I can just square them. So I have the total energy of the proton squared minus the rest energy of the proton, E rest squared, must equal to the total energy of the pion squared minus the rest energy of the pion squared. Right? So it basically boils down to that. The total energy of the proton, which is equal to the kinetic energy plus the, so we already know that actually the total kinetic energy of the proton, right? That's equal to 938 plus 5.3, right? So then when you add that, this to this, that gives you the total energy of the proton. So that's going to be 943.6. This is 943.6 squared. The rest energy of the proton we already know. That's the 938.3. And then that's squared. The total energy of the pion is the 139.6 plus the kinetic energy of the pion. So 139.6 plus the kinetic energy of the pion, quantity squared, minus the rest energy of the pion, which is 139.6 squared. Okay? So let's see here how we can solve this. I didn't put the units on all of them since they were all in units of mega electron volts anyway, right? So the kinetic energy came out 32 mega electron volts. Then you add that to this. The rest energy of the original particle is 1083.2 plus the kinetic energy. So then it's going to be the rest energy of the original particle, which wasn't moving anyway, right? So then you look up a data table and you see that actually is the lambda particle. Lambda 0, right? And it is chargeless particle, lambda 0, and it has a natural rest energy of 1115.2 mega electron volts. In other words, this decay is permitted. It's permitted for the lambda to decay to proton plus the pion because of energy and momentum conservation. Of course, it also has to obey charge conservation, strangeness conservation, lepton conservation, and baryon number conservation. So other conservation, but simply based on charge and energy and momentum conservation, this decay is permitted, and the answer comes out to be lambda 0, right? Let's say the problem had also asked us to calculate the velocity of the pion and the velocity of the proton. How would we do that? How would we calculate their velocities? Okay, so I can show you then, I'm going to use this equation. Kinetic energy is gamma minus 1 m0 c squared. Okay, so let's say I wanted to calculate the velocity of the pion. So the kinetic energy of the pion we found out to be equal to 32 mega electron volts, right? 32 mega electron volts, and that's equal to gamma minus 1 m0 c squared. So what is the m0 c squared? That is the rest energy of the pion, right? What is the rest energy of the pion? We had earlier 139.6. So this is 139.6 mega electron volts. So what does that mean? That means gamma minus 1 is 32 divided by 139. And the mega electron volts cancels, right? So 32 over 139.6. And then I add 1 to that. So that means the gamma factor is, square both sides, 1.229 squared, 1 over 1 minus v squared over c squared, cross multiply, 1 over 1.229 squared, right? I get 0.58. So v over c is equal to 0.58. That means the pion particle is going 58% of the speed of light. That's typical for particle physics problems, right? These particles are going very, very fast. So that's going 58% of the speed of light. How fast is the proton going? Okay? In this. Okay, and then the rest energy of the proton, 938.3. Then I divide them, 938.3. Then I do similar steps. I add 1 to that, right? I add 1 to this, so then I get here, I get 0.11, about 0.11. V over C is 0.11. So the proton is going 11% of the speed of light, whereas the pion is going 58% the speed of light. So it makes perfect sense. The heavier particle goes slower by about a factor of 5, right? So the proton is going 0.11 the speed of light, the pion going 0.58 the speed of light. So now you can see a good dynamics problem involving relativity, but then apply that to the field of particle physics, where particles tend to be going very, very fast anyway, so we have to apply relativity to analyze particle physics problems, okay? Thank you very much.